Hi, welcome to the Buspin uh, Reading Club and Journal Club. Today I will be presenting this article named Experimental Demonstration of Skyrmion Enhanced Strain-Mediated Physical Reservoir Computing System. The authors are as follows: Yimeng Sun, Tao Lin, Nale, et al. Um, First, I will give a short introduction to the paper and the physical concepts behind it. Um, So this article involves a small bit of artificial intelligence, so I should probably give a small introduction to that. Recurrent neural networks, RNNs, are a class of neural networks that allow previous outputs to be used as inputs while having hidden states in between. This allows RNNs to exhibit complex temporal dynamic behavior. But of course, it makes the training process way harder than convolutional neural networks. The reservoir computing framework uh, maps input signals into a higher dimensional computational spaces through the dynamics of a fixed nonlinear system called a reservoir. The fix is the important part here. Then the reservoir is treated as a black box, and the training is performed on a smaller set of weights associated with feed-forward connections between the bulk of the network, meaning reservoir, and the output layer. So the reservoir projects inputs to a higher dimensional space, and the training is only done on the output layer, meaning it's a pretty much linear regression. So, of course, the need for potentially much larger network reservoir typically worsens the computational resources and inference time requirements needed for successful training. So, of course, additionally, as the transistor production limits approaching the 3 nanometer limit, the standard silicon-based computation, Boolean computing can't be scaled much to accommodate this need for computation. So here we will present, and this article presents, physical systems as reservoirs. Physical systems are suitable candidates for reservoirs because of their natural complexity, nonlinearity, high dimensionality, and short-term memory. These three concepts are at the heart of the reservoir computing. Physical a large variety of physical reservoirs have been proposed and demonstrated, including electronic, photonic, mechanical, bacterial, spintronic reservoirs. Of course, we will focus on spintronic ones. Among these, spintronic reservoirs are appealing for scalable and low-power physical implementations of reservoir computing due to their non-volatility, non-linearity, and CMOS compatibility. In the spintronic realm, spin torque nano-oscillators, spin waves, dipole-coupled nanomagnets, and magnetic skyrmions have been proposed for realizing these physical reservoirs. Magnetic skyrmions exhibiting small size, meaning sub 10 nanometers, and their high energy efficiency and their topological stability show exclusive advantages for implementing a reservoir regarding its nonlinear response, short-term memory, and complex interactions between multiple skyrmions. Uh, Recently, Skyrmion-based reservoirs have been successfully demonstrated to realize the benchmark tasks, including standard Boolean logic operations, pattern recognition, chaotic series forecasting, etc. And we will be focusing on pattern recognition and chaotic series forecasting in this paper. Now, let's give a very short introduction about what is a skyrmion. Magnetic skyrmions are small swirling topological defects in the magnetization texture. Uh, they can be defined by the topological number S, and here's a big formula for it, which is a measure of the winding of the normalized local magnetization. Of course, there are many more details about skyrmions, and they are very complicated quasi-particles, but this small overview is enough for this paper. And additionally, in this paper, only Neal-type skyrmions are used. Previously, either the electrical currents or magnetic fields are served as inputs to those skyrmions, which is not really suitable for ultra low energy costs. In this paper, strain-mediated voltage-controlled skyrmion RC block, RC meaning reservoir computing, employing the nonlinear breathing dynamics has been proposed. Then the breathing dynamics will be explained in detail. With an estimated energy dissipation of 15 femtojoules per single input, which is 3 or 4 orders of magnitude lower than of standard CMOS-based reservoir. Here they proposed, the authors proposed a strain-mediated whole bar device using the electric field as inputs, as you can see on the figure, and the enamel's Hall effect response as outputs that are all electrical voltage signals. So the input and output not being electrical currents or magnetic fields is very efficient for low energy costs. A whole bar device fabricated on a PMMPT substrate functioned as a physical reservoir. This substrate is a very special new generation piezoelectric material that we will use the inverse piezoelectric process on it. So it's quite important. The bottom panel of the figure illustrates that electric field induced compressive in-plane strain, which could change both the magnetization, capital MC, and the longitudinal resistivity rho XX. This strain is caused by the inverse piezoelectric effect. Now, of course, we should give a short introduction to anomalous Hall effect because it is quite important. Of course, first, the ordinary Hall effect is in the figure A. The longitudinal current IX under a vertical external magnetic field contributes to the transverse voltage Vy due to Lorentz force on the carriers. So this is a pretty standard process, but the anomalous Hall effect is more interesting. The electrons with a majority and minority spin. This difference is due to spontaneous magnetization. MZ we denote it, and it's again vertical, having a opposite anomalous velocity. This majority and minority spins due to spin orbit coupling, which causes unbalanced electron concentrations at the two sides of the plate, and leads to a voltage difference Vy. The applied if electric fields generate the ferroelastic strains and further tune the magnetization and resistivity of the magnetic layers. The paper's authors suggested an empirical relationship between the Hall resistivity and other constants, such as E is the applied electric field across our substrate, and the constant R0, Rs, and A are the coefficients for the ordinary Hall effect, R0, and anomalous Hall effect, Rs, and this longitudinal resistivity, respectively. And the main point is the applied E fields, as we seen on the previous slide, both tune the magnetization and the longitudinal resistivity of the material. So this equation has two points of change in this case. Now let's quickly go over some of the results. And first, we will see the nonlinear response. Authors show the nonlinear response of the system, and then we will inspect the waveform characterization, waveform recognition task, and the time series prediction task. First, the nonlinearity of the magnetization. Authors want to show the nonlinearity of these concepts because a reservoir should behave nonlinearly in general. So the magnetization change under the application of electric field are studied using magneto-optical Kerr effect. This process is used to measure magnetization using light, using polarization of the light, and corresponding loops are shown in this first figure. The transition of the magnetic states of our device from the labyrinth domains in the first image to skyrmions in the second image, and finally to the saturation state when increasing the magnetic field are further confirmed by these images taken by a Lorentz transmission electron microscopy device, LTEM. By the way, of course, the films in this device were grown by magnetron sputtering, and the layers can be seen in the inlet in the top right figure. When electric field is applied, the magnetization nucleation fields increase significantly from 100 to 150 milliteslas at electric field equals 20 kilovolts per centimeter, indicating that the skyrmion states are modified by the applied E fields. You can see in detail in the inlet at the figure A. So as shown on the upper insets of the figure A, the two MFM images, MFM meaning magnetic force microscopy images are taken under the magnetic field of 90 milliteslas with no voltage applied for the first image and 10 kilovolts per centimeter electric field applied in the second image. Upon applying and increasing the electric field, the skyrmions start to nucleate, as we can see in the two different images. And a low density skyrmion phase evolves into a high density skyrmion phase. This fact is a crucial importance for this paper. To investigate the relationship between magnetization and the electric field, we extract the remnant magnetization M over MS from the figure A at two different magnetic field external magnetic fields. One is 200 milliteslas corresponding to a saturated state, and one at 90 milliteslas, which actually is right on skyrmion state. So of course, in this remnant magnetization, MS denotes the saturated magnetization, as shown. Comparing the skyrmion area change and the magnetization change in the first figure A, and figure B, authors conclude that the magnetization decrease comes from the skyrmion density increase with the E field applied. As we can see, the yellow part in the figure B corresponds to our our region used in the classification task. So as we can see, as a E field increases, the magnetization decreases at the Skyrmion state. At 90 milliteslas, the Skyrmion state, the typical butterfly shape is observed, indicating the strain-mediated modulation of the Skyrmion phase, realized by our structure. Of course, as you can see, this behavior is nonlinear. Such a nonlinearity of the magnetization originates from the nonlinear variation of the piezoelectric strain versus the applied E field in our heterostructure. Now we are done with the nonlinearity of the magnetization. Now we will review the nonlinearity of the Hall resistivity, the other component in our equation. And the variation of Hall resistivity rho xy with the applied E fields is measured, as shown in the figure C, by scanning a unipolar electric field from 0 to 15 kilovolt per centimeter and then back to 0 in a time period of 50 seconds at the Skyrmion state, meaning the external magnetic field is 90 milliteslas. Rho x shows a half branch of a typical butterfly shape from a piezoelectric strain. So yeah, of course we got another nonlinear behavior here, and the gray curve right below the red and blue curves. By the way, red and blue indicating the direction of the sweeping electric fields. The gray curve in this figure shows again a nonlinear rho xy variation, but this time at saturation magnetic state. Means that it is in external magnetic field equals 200 milliteslas, where the only change in the longitudinal resistivity with electric field occurs. Thus, the amplitude is smaller than of the Skyrmion state, where in the Skyrmion state, additional change of the magnetization combines with the longitudinal resistivity change. So those two concepts collide with each other. In this Skyrmion state, both the Hall resistivity rho xy and the magnetization behave nonlinearly with the input voltages. We got that from this slide and the previous slide, implying a better performance on the strain-mediated RC system. This can be expected to be better better than the saturated magnetization state. Yeah, I just told about it. This implies, of course, a better performance as a reservoir because nonlinearity and short time memory is very important for reservoirs. And now we are done with the classification. We are done with the introduction and nonlinearity phases. Now we will focus on waveform classification. This is a first task of our reservoir. Yeah. Here's in this part, the authors use a representative sequential waveform, random waveform classification task to test the performance of our Skyrmion enhanced RC system. The input signal is a random waveform sequence comprising square and sine waveforms. These waveforms, of course, are encoded as voltage and applied to the RC system. And the output signal is the anomalous Hall effect voltage Vxy, as we said previously. And so in the figure A, we can see a general schematic of our system. We have inputs, and these are random waveforms encoded as voltages, and our physical reservoir is in the middle, and the pure outputs are the voltages, voltage Vxy. The two different magnetization states, the saturation state and the Skyrmion state. We could see their effect on the first figure and the third one. These two states are behaving as two different physical reservoirs, so we can compare them. Of course, we have some MFM images again of the Skyrmion state and the saturation state. The electric field induced anomalous Hall effect voltage change. We denote that as delta Vxy of the Skyrmion state reservoir is around 3 microvolts, as you can see from the red curve at the output side. And while the saturation, the gray output signal, shows much smaller amplitudes, around 1.5 microvolts, as displayed in the figure B. Yes, sine waveforms are denoted as 1, and square waveforms are denoted as 0. And we can see the nonlinear behavior from the double peaks and single peaks and so on output red curve of the Skyrmion state, but the nonlinearity is less significant, around 15 kilovolts per centimeter, which is the limit in our case. Relatively, the memory effect in our systems can be derived from the gradual decrease or increase of the output signals around 15 kilowatts per centimeter after a series of waveforms. You can see at the bottom of our output signals, we can see the effects of the previous states, such as it resembles some of them resemble a square wave, some of them resemble a sine wave, and so on and so on. Now we can let's continue. In this part, of course, the purpose of this waveform recognition task is to recognize the current last and second to last waveform types, as we can see in this in the figure B. Black box representing the current, green box and is the last, and the orange one is representing the second to last waveform type. By using our sampled n data points for an period of output signals, and of course we will use weights trained on this system. So in the matrix representation, the orange, green, and black squares and the yellow dots correspond to those right in this slide. You can see the yellow dots on the output signal. These are sampled data points, and of course the input waveforms are denoted by the squares, and the lines in between them are for the weights. We can attach a weight to so some of those lines and get a pretty simple recognition task done. So the black, green, and orange curves in the next figure D, these figures show the recognition rates of this system for the current waveform in black, and last waveform in green, and second to last waveform in orange, as a function of n being the number of data points in an period. So we can see from this figure that for the current waveform, the recognition rates reach 100% increasing n, and it does such behavior for a very small n too. So yeah, it perfectly classifies current waveform. For the second to last one, the orange one, recognition rates are for both of the systems, both the Skyrmion state and the saturation state. They are pretty low, around 50%, and so indicating the randomness and unpredictability and this system's limits. So finally, for the last waveform, this one is a bit more interesting. Upon increasing n, the recognition rates increase rapidly with obvious randomness in it for the first n values, and they tend to saturate with n greater than 20. So the recognition rates, final saturation recognition rates are 94.4% for the saturation state and 99.3% for the Skyrmion state. So we can see that this RC device is working quite optimally and cool, I think. So yeah, and now we are done with the classification task. This is a pretty simple task. Now we will see the Mackie Glass series prediction. Mackie Glass time series is a pretty standard benchmark for RC devices. To show that the reservoirs can also implement more complex tasks than simple waveform recognition. This Mackie Glass time series is a special time series which is generated from a delay differential equation you can see on the left side, where the xt is a dynamical variable, and the parameters beta, gamma, and tau are set to obtain chaotic dynamics. So as the system is this series is chaotic, our reservoir computing device has a chance to predict that chaotic dynamics and show its capabilities. The inputs of our reservoir computing device are starting points, first few values of this MG series that are translated, amplified and translated to electric fields and given to the system as voltages. And the response of the system is recorded to form an output vector. And for getting a good evaluate the performance of this system and our training matrix, we will use a normalized root mean square error. This value is calculated on the prediction results of our training set, denoted by y prediction, and compared to the true trajectory. Now here are our results for the Mackie Glass time series. The physical reservoir receives a preprocessed sequence of electric voltage inputs. As I said, the first few values of our series, and the gray data set in the figure A, you can see the input values, and the output is obtained from the whole voltage, the animal's whole voltage, multiplied by, of course, a trained output matrix. The number of steps between the future time step and the current time step is defined as prediction horizontal step and denoted by I. Of course, our matrix training matrix the matrix we trained is different for different values of I. This yeah, and and there is an optimized algorithm that they use. Instead of only relying on the reservoirs output at the current step of the output reconstruction output vector, the authors enhance the information available for training through combining the response states at each time step with the output states from the previous time steps. So at each step, the output states from the previous time steps are used to. So it creates a better information availability. So here are our results. As you can see, the better accuracy of prediction can be achieved using our using the optimized algorithm, using not only the current state but current output, and not only the current output but the previous outputs too. So yeah, basic method means only the current output, and the optimized algorithm means the other type. And of course, we can see the improvement on the blue lines and the red lines. And in general, of course, it is more difficult to predict the later steps due to chaotic nature of these series. So it is the system works very well for I equals 1. The only predicting the next step, but it behaves not that great for the I equals 20, 20 steps afterwards. So yeah, and we can see the normalized root mean square error versus the horizontal step in the figure B. So yeah, as you can see, as I increases, the R error grows quite a lot. So and of course, these results indicate a greater potential of our physical reservoir doing a more complicated task than simple classification. And for concluding, I will be presenting the discussion part of this paper. The physical origins can be seen in these slides. And in the Skyrmion state, the Skyrmion number and size are controlled by the applied electric fields through inverse piezoelectric effect, as we have seen before. And the increase in the Skyrmion size and number contributes to the magnetization and therefore the outputs whole signal. So yeah, in these MFM images, we can see that no electric field. The Skyrmions are quite sparse and not that much around. But as the electric field increased to the +5 kilovolts per centimeter, they grow and they get quite big. But some elongated shapes are observed. And after reducing the electric field back to 0, the quantity of the Skyrmions are almost unchanged, but some elongated Skyrmions restore to round shapes. And authors study the cause of this Skyrmion deformation. We can see that this Skyrmion deformation stems from the decreasing out-of-plane magnetic anisotropy. This observation is done by again magnetic optical Kerr imaging and using rotating magnetic fields, and this concluded that the effective magnetic anisotropy fields change quantitatively with the applied electric fields, and out-of-plane magnetic anisotropy decreases with heightened E fields, resulting in enlarged Skyrmions. So yeah, this is the physical reason behind the Skyrmion enlarging. And in the study of MG time series, the output amplitude is increased in the analysis to suppress the noise. Output amplitude is at the beginning same order of magnitude in the microvolt state, but it amplitude it increased to millivolts to increase to suppress the noise. So yeah, authors suggest that using not using an magnetic tunnel junction can be a better choice, replacing the whole bar device to magnify the output signal. And here are some remarks on the power consumption. This device at this size, the original size, uses 800 nanowatts for capacitances of the crystals, and 25 microwatts for joule heating. But they suggest that 100 nanometer nanomagnet device will use from basic calculations nearly 150 picowatts, and at 1 gigahertz this nanomagnet system will consume 1 femtojoule per waveform, and this means an insanely low ultra low energy consumption. And yeah, to sum up, the strain-mediated smooth-sonic reservoir operates with all electrical input and output voltages, exhibiting compelling ultra-low power and multi-parameter fusion, and having the potential for ultra-fast operation. Thanks a lot for listening to my slide and my presentation.